basically last week we started to deal with water resources management in practice, and at the beginning you have seen some basic theoretical principle and basic setting for water resources management, for dealing with water resources management problem. And if I am not wrong, you started with optimization problems, because the classic approach in water resources management, I have a problem with the categories. The basic approach in water resources management, the classical approach, was to try to take decisions related to water resources management by using optimization algorithms that were in charge of optimizing objective functions, meaning to find the optimal solution for reaching a target. A target that at the beginning was expressed through a benefit function, an economical gain, and the task of the water resources manager was to find the solution, the decision that led to maximization of the economical income. Today, as you know, we care in water resources management not just about economic income, not just about economic benefit, but we try also to involve in the decision other targets like environmental protection, like water safety, and so on. But in any case, it's important for us to study the basis, the classical approach, which relies, as I said, on optimization theory. And just to give you an overview that probably my colleague already gave to you, today the problem is still solved through optimization algorithms that are in charge of identifying the best solution, expressed in some way according to some criteria. Usually these algorithms are applied through softwares that are available. Some of them are even public domain softwares. And therefore, in the current situation, we don't have to care much about the solution that the software uses for identifying the best alternative, the best possible decisions. We just give to the software an input, the constraints, we tell the software what the situation is, and then the software finds, usually very efficiently, because these algorithms are very efficient, the software finds the best solution. As I said, usually we don't have to care about the method that the software uses. This approach is possible because today we have at disposal computational capacity that is very high, but nevertheless we should always be concerned about what the software does. And this is the reason why I think it is extremely important to study, in any case, what is the method that the software uses. Because once that we read the manual of the software, and once that we understand what is the method, the optimization method that is used, we must be able to understand what the method does. This is the reason why we still need, even if we don't care about what the software does, we still need to understand what happens, what is the method that was used to find a solution. And the reason for this, the reason why we should still know, we should still be aware of what the software does, is that if you knew the basis of a method, if you knew the basic principles of a method, you can better evaluate the results. You should always be concerned about the fact that sometimes the software gives you wrong results. This is perfectly known, even Excel. There are some examples, if you look at the web, there are examples of Excel bugs. So examples that show you that Excel sometimes makes erroneous computations. Any software is affected by bugs. So when you see the result that is given by a software, it's very important that you are a bit concerned about the reliability of the result. And you ask yourself, is this result reasonable? Is this result justified from my perspective, from my perception, my intuition? And of course, to gain a perception, to gain an intuition, you have to know what the software is doing. So you don't have to care much, but you have to care. This is the moral, the conclusion. When you use a software, you don't have to care much. You don't have really to check everything the software does, otherwise the software becomes useless. But you should be a bit concerned, a bit of care should be given to the evaluation of the results. So this is the reason why we are still teaching classical methods, and in particular the Lagrange multiplier, and you will see later on that I will discuss very briefly some other methods, some other optimization methods. The Lagrange multiplier method that you studied in the past lecture is an analytical approach, a very classical approach that is analytical. I think my colleague already told you what is the advantage of an analytic approach. The advantage is that the solution can be easily done even by hand, even without using the computer, because it's an analytical solution. The problem of the analytical solution is that you must be able to compute the derivatives of the objective function, because you have seen that you can find the solution by taking the derivatives and equating the derivatives to 0. Therefore, this means that you need to compute the derivatives analytically. And not all the objective function, of course, I would say only a small part, a small subset of the possible objective function that you will be with in water resource management can be derived, you can take the derivatives. Okay, so basically you have seen that the method of Lagrange multiplier is based on the computation of a function that is called the Lagrangian, which depends on a decision plan capital X and a multiplier lambda. And correct me if I'm wrong, I think I'm using the same notation. It's expressed by an objective function, which we indicate with the symbol MB, which depends on the decision plan, minus a multiplier lambda, which multiplies some constraint that we can express in this way. Minus lambda, which multiplies a constraint that we can express as a function gx of the decision plan minus a constant. Now, did you use the letter B or, yeah, okay, fine. Very often we can, the constraint is given by the continuity equation. The continuity equation says that if you have a number of allocation Qi, this must be equal to the total quantity of water that is available. This is usually expressed in flow per unit time. The allocation is usually expressed like in liters per second or cubic meters per second. And the sum of the allocation should be equal to the total flow per unit time that is available. Like you take some water from the river, the water that you take from the river you indicate with the symbol Q, and then the water that you allocate, sorry, this is Xi, I think, the notation that you used. The water that you allocate, the sum of the Xi, should be equal to the total water available Q. And therefore you can substitute here by sum T equal 1 to n, where n is the total number of local allocation of the Xi minus 2. This is the Lagrangian. And by using a special case of objective function, net benefit function, which, if I'm not wrong, is given by mbx equal to sum I equal 1 to n A1, which multiplies 1 minus B1 minus let me see if I remember 1 minus exponential minus B1 psi. I think it was, this one was objective function that you considered. By using this special case of objective function, you obtain a problem that that can be easily solved analytically with the method of the Lagrange multipliers. Because you can take the derivative of this function quite easily. And you already know, in this special case, how to solve the problem, how to identify the best decision, so the best xi, depending, of course, on the parameters a1 and b, ai and ei of the objective function. Now, what I would like to do today is to introduce another special case in which the constraint here, this one, is not expressed through an equality. So it's not an equality constraint, but it's an inequality constraint. This is another case that I would like to deal with, and then we will pass to an exercise to show you how the method can be applied in practice with real numbers. So let me now deal with the case of inequality constraints. What do I mean with when I say an inequality constraint? An inequality constraint, for instance, is expressed in the form sum of the xi should be less or equal than q. And this is a kind of constraint that is typical in water resources management. This is the reason why I would like to show you this example. Because usually we are not forced to allocate exactly the total amount of water. We are forced to allocate a quantity of water that is less or at most equal to the total amount. Because if we allocate less water, it's not a problem for us than the total amount. The problem is that we can't allocate more water, but we can allocate less water or at most the same amount of water. So this constraint is more typical in water resources management than the equality constraint. So it's interesting to see how we can deal with this type of constraint. Of course, the situation becomes a bit more complicated, as you can understand. And therefore, the first solution that may come to our mind is to transform the inequality constraint in inequality constraint. How can we do that? How can we transform, I say again, an inequality constraint to an equality constraint? We can do that by introducing an additional variable, a dummy variable. Dummy means in English a variabile fittizia. So we can introduce a dummy variable, which is, we can call it the symbol W, and with this dummy variable I can write the inequality constraint in this way: sum of the xi plus w squared equal to q. W is squared in order to be sure that it's positive. So, you see that if we admit that W is a variable, for varying W, you obtain allocations that are less than the total amount Q, or at most equal for W equal to 0. If you put W equal to 0 in this relationship, you obtain an equality constraint. If W is different from 0, then you get an inequality constraint because the total amount of the xi is lower than q. So you see that in principle, we can do that. We can transform an inequality constraint in an equality one. The only problem is that we introduced an additional variable W. This is not a constant, it's a variable. Because in order to keep the original constraint, we have to allow W to vary. Fine. Then we can rewrite the Lagrange in this way. We can write the Lagrange as the sum of MB x minus lambda, and then I write again here sum for e equal to 1 to n of the xi minus q plus w squared. This is the new Lagrange. Let me write again Lagrange depending on capital X lambda. Okay, then let's try to solve the problem. The problem is solved in the same way as before, but there is one but. There is an additional variable in this Lagrange, and therefore there is an additional unknown W. Therefore we need an additional equation. The additional equation can be obtained by equating to 0 the derivative of the Lagrange with respect to W. Therefore we can write an additional equation, derivative of the Lagrange depending on x and lambda with respect to W. Now, the net benefit function doesn't depend on W. So the derivative of this first term at the right-hand side is just 0. So I don't write it. Then we have the derivative of the second term at the right-hand side, which is given by the sum of 3 terms in turn. The first term is the sum of the xi, which doesn't depend on W. The second term is q, which doesn't depend on W. The third term is W, which depends on W. So basically the derivative is given by the derivative of the product lambda W squared with respect to W. So we have minus, and then we can write the derivative of lambda W squared with respect to W, which is equal to minus 2 lambda W, which should be equated to 0. This equation has two solutions. The first one is lambda equal to 0. The second one is W equal to 0. There are two solutions to this additional derivative, additional equation. Now let's try to understand what do this solution mean. First of all, if W is equal to 0, it means that we go back to the case of the inequality constraint. If you look at the Lagrange, if W is equal to 0, you get the same constraint, the same Lagrange that you dealt with on Tuesday. So you go back to the original case. What does this mean in practice? It means that you obtain the maximum benefit if you allocate all the valuable water, which is often the case, because usually in water resources management, the more water you allocate, the greater your benefit. And therefore, this means that even if you you add an inequality constraint, you end up by allocating all the water. This is the physical meaning of the case W equal to 0. So if you end up with this case, then this means that you just take the solution that is given by the previous exercise with the equality constraint. But this is an option. So pay attention. The first option that we have is to consider the solution given by the equality constraint. So the first option is, let's forget about the inequality constraint. Let me suppose that it's inequality, and then I find the solution, which I can find because I know from the previous class how I can estimate it. And this is the first option then, W equal to 0, but we have another option. The second option, of course, corresponds to W different with respect to 0, which means that you get your benefit, you get your maximum benefit by allocating less water than available. This is reasonable from a practical point of view, because sometimes when you allocate more water, you increase the costs, like maintenance costs. If you put in the pipes too much water, maybe that you have to take care that the pipes doesn't leak, some additional maintenance costs. So sometimes it may happen that if you allocate more water, the additional costs are greater than the additional benefit. So this situation in which it's more convenient for you to give less water than the total amount could be reasonable. And this would be given, as I said, by the second option. Second option, which means, I say again, that W is different with respect to 0. So in this situation, you have lambda equal to 0. What does this mean from a practical point of view? This means that in your Lagrangian, the old Lagrangian that you considered on Tuesday, you don't have the constraint. And again, this is reasonable, this is perfectly understandable, because if you have your higher convenience in allocating less water than available, then what's the reason for putting the constraint? Let's just solve the problem without constraint. The maximum benefit will be obtained for a solution that corresponds to less water than available. So basically, you end up with two possible options, two possible solutions. Of course, one of them will give to you a benefit that is greater than the other, and this will be your final solution. So, before trying with an exercise which clarifies better the situation, let me summarize and say that when you have an inequality constraint, then you have to solve the problem twice. Once without the constraint, and once by using the equality constraint. Then you find the solution to benefits, and then you choose the solution that gives to you the higher benefit. So basically, the complication was that from one single exercise, you turned up with two exercises. And think about the situation in which you may have more than one constraint. So with the Lagrangian multipliers, you may have a situation in which you have like 5 constraints. If you have more than one constraint, then you have to write the Lagrangian by including all the additional constraints with a different value of the multiplier. Each constraint must have its own multiplier. So if I have here two constraints, I divide lambda 1, which multiplies the first constraint, minus lambda 2, which multiplies the second constraint. And then I have to take the derivative of the Lagrangian with respect to lambda 1 and lambda 2. So any constraint introduces an additional equation and therefore introduces an additional complication. If the constraint is an inequality constraint, any additional constraint introduces two additional solutions, not just one, because for any constraint you have to consider the solution lambda equal to 0 and the solution w equal to 0. All the possible combinations of the possible solutions, and therefore it becomes difficult to manage in practice. So, the moral of the story is, in principle, it's not a conceptual complication if you have inequality constraints, but it's a practical complication which can be difficult to manage if the number of constraints increases. This is, in general, the problem of the analytical methods. They give you an exact solution. They usually are very fast. Even if you use the PC, an analytical method, it is much faster than a numerical method. The problem is that analytical methods are simple to use only in a limited range of cases. Once that you introduce complications, analytical methods become difficult to manage, and the numerical solution is preferable. Okay, now let me give to you an exercise. Unfortunately, I printed out the exercise on a paper, but I forgot it in the office, so I have to turn the PC on and get the exercise from there. It's a very simple exercise which clarifies how Lagrange multiplier works in a very effective way, so I think it's worth developing it also for relaxing a little bit. Give me just 1 minute. More than 1 minute. attimo solo che devo trovarlo. Okay, so let's see the test that is very simple and then we solve. Okay. Okay, so this is an example of objective function. We just need to copy it and then with three decision variables. It's an objective function that is different from the one that you already considered. And there are three decision variables. So the benefit is given by the sum of three benefits that correspond to any user. So the first one depends on Q1. The allocations are given with the symbols Q1, Q2, and Q3, not X as before. So the first benefit is given by 12 Q1 minus Q1 squared. And this is the benefit for the first user. The benefit for the second user is 8Q2 minus Q2 squared, I think. Yes, and the benefit for the third user is given by plus 18Q3 minus 3Q3 squared. So, this is the benefit function. Again, let's have a look at the type of function that is this one. You see that for each user, you have a positive term, which gives indeed the gain that the user gets when water is allocated to him. But then we have a negative term, which is a cost term, which depends typically on the square of the allocation. On the square because if you think about the losses of energy in pipes, they depend on the square of the flow. And therefore, usually, when you have to pay for the energy that is needed to push water in the pipes, you pay depending on the square of the flow, because again, the losses, the energy losses depend on the square. So if you have to use hydropower for energy power for making the pump working, of course, usually the cost of the power depends on the square of the flow. You can already understand that the fact that the cost depends on the square of the flow determines a situation in which for a given limiting value of the flow, you may have the costs that are higher than the gain. So probably, in this case, the maximum benefit doesn't correspond to the maximum allocation of water, but corresponds to a given value of the allocation, such that if you exceed this allocation, you get costs higher than the gains. So the first question of this exercise is to find the solution in terms of allocations Q1, Q2 and Q3 that gives to you the maximum benefit without any constraint. So let's suppose that we have an unlimited amount of total water available. Let's identify the Q1, Q2 and Q3 that give the maximum benefit. In doing so, if you don't have any constraint, the Lagrange is simply equal to, you even don't have to write any Lagrange, you just compute the maximum by equating to 0 the derivative